Hello dear students, welcome to the chapter number 8, Current Electricity in Physics. In this chapter, topics are omitted: experimental verification of Ohm's law, derivation of expressions for equivalent resistance. These two portions are omitted in this chapter. So let us start this chapter. Our first topic is concept of charge. In your previous class, you have learned that when two non-conducting bodies are rubbed together, there is a transfer of electrons from one body to another. And we say that one body is charged by rubbing. So, we can say that charge is flow of electrons from one body to another. Charge is of two types, positive charge and negative charge. Two like charges repel each other while two unlike charges attract each other. The symbol of charge is small q or capital Q. And unit of charge is coulomb, which is symbolized by capital C. Concept of current. Current is defined as the rate of flow of charge. It is symbolized by the letter capital I or small I. I equals to Q upon T, where I is the current, Q is the charge flowing in the conductor, and T is the time. Current is measured by an ammeter by connecting it in series in that circuit. Unit of current. Unit of current is ampere and its symbol is A. So we define 1 ampere is the current which flows in a conductor when 1 coulomb of charge passes through it in 1 second. That is 1 ampere equals to 1 coulomb upon 1 second. In metals, the moving charges are the free electrons, and in electrolytes and ionized gas, charge is carried by charged ions, that is cations and anions. If n electrons passes through a cross section of a conductor in time t, Q equals to Ne. Hence current I equals to Ne upon T. Current is a scalar quantity, and if in an electrolyte N1 cations are there and each is carrying charge Q1, and N2 anions are there and charge Q2 is carried by each anion, then the current is calculated by the formula N1Q1 plus N2Q2 upon T. If two charges, whether they are like or unlike charges, if they are brought near each other, some work is always obtained due to their repulsive or attractive forces. So, the potential at a point in a region of charges is measured in terms of the work done in moving a test charge from a point of zero potential to that point. So we can define potential, that potential at a point is defined as the amount of work done per unit charge in bringing a positive test charge from infinity to that point. It is denoted by the symbol V. It is a scalar quantity. In case of two like charges, the potential is always positive since we get the work done against the repulsive forces, while in the case of unlike charges, due to attractive forces, the potential is measured as negative. Here we are having a body which is positive charge, and a test charge is brought near this body from the infinity. If W joule of work is done in bringing this test charge Q from the infinity, then the potential at point P is equals to V equals to W upon Q. Unit of potential is volt, which is equals to 1 joule per coulomb. The potential difference between 2 points is equal to the work done per unit charge in moving a positive test charge from one point to the other. Potential difference is also a scalar quantity, and if W joule of work is done moving in a test charge Q from point A to a point B, then potential difference VA minus VB equals to W upon Q. The unit of potential difference is also volt. Potential difference is measured by a device called voltmeter, which is connected in the parallel in the circuit. Concept of resistance. The obstruction offered to the flow of current by the conductor or wire is called its resistance, and the cause of resistance is when a metal is formed, its atoms loses some electrons from its outer orbit. These electrons are called free electrons, and they can move from one point to another in the metal. In the first image, you can see that there are positive ions and electrons in the metal wire. Since there is no potential differences applied, the electrons are moving in a random position and they are striking with the positive ions and the walls of the metal. In the second image, you can see that when potential difference is applied, electrons are moving in a direction and they are constituting a current in the metal wire. In the first image, value of current is 0, and in the second image we are obtaining some current. This process continues and the electrons do not move in bulk with a continuously increasing speed, but there is an overall drift of electrons towards the positive terminal. Thus, a metal wire offers some resistance to the flow of electrons through it. Ohm's law. According to Ohm's law, the current flowing in a conductor is directly proportional to the potential difference applied across its ends, provided that the physical conditions and the temperature of the conductor remain constant. So, if a current I flows in a conductor when the potential difference across its ends is V, then I is proportional to V, or V upon I equals to constant. Now we are having the formula V equals to IR, where R is the resistance of the conductor. The unit of R is volt per ampere or ohm, and it is in the honor of scientist Ohm. It is denoted by the symbol omega. For higher resistance, we use units 1 kilo ohm or 1 mega ohm. Conductance. The reciprocal of resistance is called conductance and its unit is ohm inverse or Siemens, and its symbol is S. Here you can see a graph which is plotted between V and I for a metallic conductor. For a metallic conductor, we always get a straight line which is passing through the origin of the graph. Slope of IV graph. Slope of IV graph is del I upon del V, which is equals to 1 upon resistance of the conductor. Limitations of Ohm's law is the temperature of the conductor remains constant. If temperature is changing continuously, then the Ohm's law will not be applied. Ohmic and non-ohmic resistors. Ohmic resistors are those resistors which follow the Ohm's law. These are all metallic conductors: nichrome, copper sulfate solution, with copper electrodes, dilute sulfuric acid, etc. at a constant temperature. And non-ohmic resistors are those which do not obey the Ohm's law. Examples are LED, solar cell, junction diode, transistor, filament of a bulb, etc. Here you can see a graph which is plotted for ohmic and non-ohmic resistors, and we are obtaining a straight line for the ohmic resistors and a curve for non-ohmic resistors, since the value of V and I are changing accordingly for non-ohmic resistors. Factors affecting the resistance of a conductor. These are material of conductor, length of conductor, thickness of conductor, and temperature of conductor. Number 1, dependence on the material of conductor. As we know that different materials are having different concentration of free electrons, that's why they offer different amount of resistance during the flow of electrons. Since good conductors are having large concentration of electrons, hence they offer less resistance, therefore they are good conductors. On the other hand, the insulators or non-conductors like rubber, glass, etc. are having negligible concentration of free electrons, and that's why they offer high resistance, so they are called insulators of electricity. Dependence on the length of conductor. In long conductor, we know that number of collisions will increase for the free electrons. So if we are increasing the length of a conductor, we are having more resistance. That's why R is directly proportional to L. If the length of a wire of the same radius is doubled, the resistance of wire also gets doubled. Dependence on the thickness of conductor. If we are having a thick conductor, we are providing larger cross-section area for the electrons to flow in the conductor. That's why resistance is inversely proportional to cross-sectional area. Dependence on the temperature of conductor. With the increase in the temperature of a conductor, the random motion of electrons also increases because their kinetic energy is also increased. Hence, if the resistance of a conductor increases with an increase in its temperature. Here is a graph, VI graph of a conductor at two temperatures T1 and T2, and you can see that the line A is steeper than the line B, because the line A is showing that at higher temperature you are obtaining higher resistance, and line B is showing that At lower temperature you are having a low resistance, a specific resistance. Since we know that R is proportional to L, where L is the length of the conductor and R is inversely proportional to A, where A is the cross-section area of the wire, if we are going to combine these two equations, we are having R equals to rho L upon A, where rho is called the specific resistance or resistivity of that conductor. The unit of rho is ohm meter and it's different for different materials. The factors affecting the specific resistance. The specific resistance of a substance is its characteristic property and it is different for different substances. The specific resistance of a substance depends on its temperature. As temperature is increasing for the metals, it will decrease with the increase in temperature for semiconductors. For some alloys like constant and manganese, it remains practically constant with the change in temperature. Conductivity is the reciprocal of specific resistance and it is denoted by the symbol sigma. Its unit is ohm inverse meter inverse. Now, how we choose a material for a wire, for a connecting wire or a resistance wire? The factors are the wires used for electrical connections and for power transmissions are having least possible resistance. Due to low or negligible resistance of a connection wire, the current in the circuit remains unaffected. Hence, we use copper or aluminium for the connecting wires because their specific resistance is very low. The resistance wire or standard resistance, we use for them the alloys like manganese and constantan because they are having high resistance and their resistance does not change with the change in the temperature. A fuse wire. For a fuse wire, we use an alloy made of lead and tin since its melting point is low and its specific resistance is very high in comparison of copper and aluminium. So it permits current up to its safe limit to pass through it, but an excessive current melts it so that it blows off the filament of an electric bulb. A tungsten wire is used because it has a high melting point. The heating element in appliances such as heater, toaster, oven, etc. A nichrome wire is used because the specific resistance of nichrome is high and its resistance increases to a great extent with the increase in temperature. So it converts electrical energy into heat energy. Superconductors. Superconductors is a substance of zero resistance or infinite conductance at a very low temperature. For example, if mercury is used below a 4.2 Kelvin temperature, it behaves like a superconductor. Similarly, lead below 7.25 Kelvin and niobium below 9.2 Kelvin behaves like a superconductor, but practically superconductors are not possible to obtain since it's not possible to maintain such a low temperature. Electromotive force of a cell. Here you can see a cell in an open circuit where we have taken dilute sulfuric acid as an electrolyte and zinc and copper electrodes are taken. Since dilute sulfuric acid will dissociate in positive ions H plus and negative ions SO4 minus 2. So the negative ions impart electrons to the zinc electrode and the positive ions gain electrons from the copper electrode. This chemical action creates a difference in concentration of electrons between these two electrodes of the cell. Hence a potential difference called the electromotive force is created between the two electrodes of the cell. So we can say that when no current is drawn from a cell, that is when cell is in open circuit, the potential difference between the terminals of the cell is called its electromotive force or EMF. It is denoted by the symbol epsilon here. Unit of electromotive force is also volt and it is symbolized by capital V. So the EMF of a cell is also defined as the energy spent or the work done per unit charge in taking a positive test charge around the complete circuit of the cell as well as in the electrolyte inside the cell. If W work is done taking in a test charge Q around the complete circuit of the cell, then epsilon equals to W upon Q. The factors affecting the EMF of a cell are the material of the electrodes and the electrolyte used in the cell. When cell is in a closed circuit, that is, we are drawing current from the cell, The potential difference between the electrodes of the cell is known as its terminal voltage. It is denoted by capital V and its symbol is also volt. So the terminal voltage of a cell is defined as the work done per unit charge in carrying a positive test charge around the circuit connected across the terminals, that is over here. If W dash is the work done in carrying a test charge Q around the circuit, then V equals to W dash upon Q. Voltage drop in a cell. We know that the terminal voltage is always less than the EMF of the cell, since the amount of energy spent in the flow of charge through the electrolyte inside the cell. So if W is the work done or energy spent in carrying a test charge Q through the electrolyte inside the cell, then the voltage drop in the cell V equals to W upon Q. Relationship between EMF and terminal voltage of a cell. If W is the work done in moving a test charge Q outside the cell as well as inside the cell, and W dash is the work done in moving a test charge Q outside the cell, and small w is the work done in moving the test charge Q inside the electrolyte of the cell, then we know that W equals to W dash plus W. If we divide the above equation by Q, we get W upon Q equals to W dash upon Q plus small w upon Q. And we know that from the definitions of EMF, terminal voltage and voltage drop, that W upon Q equals to epsilon, W dash upon Q equals to V, and W upon Q equals to V. Hence, from the equation 2, we are getting the equation epsilon equals to capital V plus small v. Thus, when current is drawn from a cell, its terminal voltage V is less than its EMF epsilon by an amount equal to the voltage drop small v inside the cell. Internal resistance of a cell. When a cell is in a closed circuit, the current is flowing inside the cell as well as outside the cell. Inside the cell, it is flowing in the form of cations and anions, and outside the cell, it is flowing in a metallic wire in the form of free electrons. For the external circuit, current is flowing from anode to cathode, and for inside the cell, it is flowing from cathode to anode to maintain a constant potential difference. So the resistance offered by the electrolyte inside the cell to the flow of current is called the internal resistance of the cell. It is the internal resistance of the cell due to which its voltage drops on drawing current from it. It is denoted by the symbol R and its unit is ohm. Hence V equals to capital IR. For circuit analysis, the internal resistance R of a cell is considered to be connected in series with the cell. The internal resistance of a cell is represented by following figure. Now, relationship between EMF, terminal voltage and internal resistance. Here we are having a circuit diagram where R is the resistance in the external circuit, cap small r is the internal resistance of the cell, epsilon is the EMF of the cell, and capital V is the terminal voltage. We are drawing here current I from the cell. So total resistance of the circuit is R plus R. Current drawn from the cell is I equals to EMF upon cell upon total resistance, that is epsilon upon R plus R. So EMF of cell equals to I into R plus R. The terminal voltage of the cell is capital V, hence V equals to IR, and voltage drop equals to V equals to IR. So epsilon equals to V plus small v. Factors affecting the internal resistance of the cell: the surface area of the electrodes, the distance between the electrodes, the nature and concentration of the electrolyte, and the temperature of the electrolyte. Now, combination of resistors. In order to have a desired resistance in a circuit, we connect two or more resistors together in three types of combinations. First in series, second in parallel, and both in series and parallel. To increase the resistance, we combine resistors in series, and to decrease the resistance, we combine resistors in parallel combination. In combination of resistors in series, we combine the three resistors or four or more than it in this system. Here we are taking the first resistor R1 and its end point is connected to the first end of the second resistor. The second end of the resistor is connected to the first end of the next resistor, and like this we have created a combination of resistors in series. In these type of resistors, the value of I does not change throughout the circuit, and the value of the resistance is increased if we are desiring a higher resistance for the circuit. For a series combination, there are two facts, that is, the current has a single path for its flow, hence same current passes through each resistor. Hence the potential difference across any resistors is directly proportional to its resistance. So the potential difference is different across different resistances. The potential difference across the entire circuit is equal to the sum of potential differences across the individual resistors, that is V equals to V1 plus V2 plus V3 and so on. Expression for the equivalent resistances combined in series. Derivation of the formula is not required, it is omitted in your syllabus. If we are having different resistors of different resistance, we are having Rs, that is equivalent resistance, equals to R1 plus R2 plus R3 and so on to Rn. Combination of resistors in parallel. In the parallel combination, one end of each resistors is connected at one point and the other end of all the resistors is connected at the next point of the circuit. Here the value of I changes in each resistor, but the value of V is unchanged throughout the circuit. So the two facts that are to be noted about the parallel combination is that the potential difference across each resistor is the same. The current in a resistor is inversely proportional to its resistance. The sum of currents is I1, I2, I3 in the separated branches of the parallel circuit is equal to the total current I drawn from the sources, that is I equals to I1 plus I2 plus I3. For the equivalent resistance combined in parallel. If we are having different resistors of capacity R1, R2, R3 and Rn so on, so we are having the equivalent resistor 1 upon Rp equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on to 1 upon Rn. Derivation of the formula is not required. Combination of resistors both in series and parallel. Sometimes to obtain a desired value of resistance from the given resistors, we connect some resistors in parallel and then this parallel combination of resistors is connected in series with some more resistors. After this, we find the total resistance by adding each resistance and the equivalent resistance of each parallel combination connected in series. So dear students, this is the first part of the chapter Current and Electricity has been completed. We'll meet in the next part of the chapter. Till then, take care.